Hey everyone, and welcome. Today we are pulling back the curtain on something that's at the very heart of so many AI systems. We're going to find that one simple, elegant yes or no switch that lets AI make these massive decisions, from something tiny to something that could literally save a life. I mean, just think about your email. Every single morning, a decision is being made for you, over and over again. Is this message actually important, or is it just junk? It's a simple choice, right? A fork in the road.
Or what about when you're traveling? Behind the scenes, there are these systems constantly making predictions. Is this flight going to be on time or is it going to be delayed? And that's not just a wild guess, it's a calculated probability.
These little choices are absolutely everywhere, from doctors using AI to classify a tumor as cancerous or benign, to traders predicting if a stock is going to go up or down. And believe it or not, there's one foundational tool that powers almost all of them. So let's see how it actually works.
Okay, so this tool is called Logistic Regression. Now, I know, the name sounds super technical and intimidating, but don't let it scare you. It's actually this incredibly elegant solution that's shaped like a gentle S. And it's built for one thing, answering these yes or no questions. So what's the big deal here? Well, imagine you're trying to predict how a student will do on an exam. An older method, called linear regression, would try to guess their exact score. Like 58.5 points, which is kind of useful. But what do we really care about? We care if they passed or failed, right? And that's exactly where logistic regression shines. It doesn't give you a score, it gives you a probability, like an 80% chance of passing.
And this right here, this is the magic behind it all, the S-curve, or if you want to be fancy, the sigmoid function. The idea is so powerful because it's so simple. No matter what crazy data you throw at this thing, age, blood pressure, how many hours you studied, it takes that input and it squishes the output into this nice, tidy probability between 0 and 1. 0 means no way, it's impossible. 1 means it's an absolute certainty.
Okay, so how does the AI learn where to put a new data point on this curve? How does it learn to make a good judgment? Let's break that whole process down.
It's basically a 4-step recipe. First, we collect a bunch of data that might be important, like a student's attendance record. Second, we look at past results and label them. We tell the machine who passed, we call that 1, and who failed, which is 0. Third, the model trains itself. It just keeps adjusting that S-curve over and over until it finds the one that best explains what happened in the past. And finally, and this is the most important part, we set a rule for making the final call. And that rule is called the threshold. It's the line in the sand. Most of the time, we just set it right in the middle, at 50%. So if the AI calculates a student's probability of passing is more than 50%, it says, yep, they'll pass. If it's less than 50%, it predicts, nope, they'll fail. It's as simple as that. It's basically the AI's version of a gut check.
Now, this whole idea isn't just for predicting grades or filtering spam. Let's look at a really high-stakes, real-world example where this S-curve can literally be the difference between life and death. So way back in 1948, this huge study started in a town called Framingham, Massachusetts. Over 5,000 healthy adults signed up to be monitored for decades, all to figure out what common factors lead to heart disease. The data from that incredible long-term effort is now the fuel for the very prediction models we're talking about today. And what does the model look at? Well, it looks at things about you. Your age, your gender, whether you're a smoker, your cholesterol levels, your blood pressure. All of these little data points are fed into the logistic regression model to calculate one single critical probability, your risk of developing heart disease in the next 10 years.
So, the model takes in all this health data and spits out a number, a probability. But that brings us to maybe the most important question of all. How in the world do we know if its prediction is actually any good? I mean, we can't just take its word for it, right? Especially not when we're talking about someone's health. We need a way to grade its performance. We need to give it a report card. And this is that report card. It's called a confusion matrix, which is a funny name, but it's super useful. Let's walk through it. So the model did some things well. It correctly identified 15 people who actually did get heart disease. We call those true positives. Great. It also correctly identified 918 people who were healthy and stayed healthy. We call those true negatives. Awesome. But now let's look at the mistakes, because that's where things get interesting. It wrongly flagged 8 healthy people as being at risk. That's a false positive. And this is the one that really matters. It missed 157 people who did develop the disease, telling them they were probably fine. That is a false negative. So you see the key takeaway here? This matrix doesn't just tell us if the model got it right or wrong. It tells us how it got it wrong. And in medicine, a false negative, telling a sick person that they're healthy, that can be so much more dangerous than a false positive. Now, to boil all that down into a single grade, we use something called the AUC score. Just think of it as one number that summarizes how well the model can tell the difference between the sick group and the healthy group. A score of 50% is basically useless. It's just a coin flip. This model, using that Framingham data, gets a score of 73.2%. So, is 73.2% any good? Well, according to this pretty standard rule of thumb, it's fair. It's not amazing, not excellent, but it's definitely way better than just guessing. It shows the model has a real, even if it's imperfect, ability to see who's at risk. Okay, let's zoom out for a second. Why did we just spend all this time talking about one S-shaped curve? Well, it's because this simple tool is one of the most important building blocks in all of artificial intelligence. Think about this for a second. This humble little decision maker, it is the direct ancestor of the most complex AIs we have today. The giant neural networks that run our world, they're really just thousands or even millions of these simple logistic regression units, all wired together, with each one making its own tiny yes or no judgment. Seriously, without this basic ability to take in a bunch of information and sort it into one of two buckets, a huge part of what we call AI would just stop working. It really is like the atom of AI decision-making. And that leaves us with one last really tough question. We saw that the default threshold is usually 50%, but if you were the one designing a model to detect a fatal disease, would you leave it there? Would you be okay with risking those false negatives? Or would you lower that threshold, say down to 10%, to try and catch more potential cases, even if it means you'd get a lot more false alarms? The AI can give us the probability, but deciding where to draw that line, well, that's still a deeply human choice. Thanks for joining me for this explainer.